Good afternoon, everyone. Thanks for joining us in this session on MSC Apex Generative Design in Action. I'm going to start off right away since I have a lot to show you and I'm really enthusiastic about this product and I enjoy using it at home as well. So let's get started. First of all, I'd like to draw your attention to the poll in the meeting. Right at the top, I'll really appreciate it if you can quickly just indicate your level of experience with Apex Generative so that I have a good idea of who I am talking to today. So please check in the right-hand corner at the top. There's a little F and it looks like a form. If you can just indicate your level of experience, that will be much appreciated. I'm going to try my best to stick to half an hour as scheduled. But please forgive me if I run over time. I'll try my best to cover all the important things within the half hour, but we are recording the complete session, especially when it comes to the demonstrations. You know, it can take as long as you like to spend on that. So let's get going. So let's talk about the motivation for generative design and examples thereof. You may know or may have heard about topology optimization. This is the technology where material is eroded away in a systematic procedure and you end up with a result that looks more or less like shown on the screen. The challenge with this, however, is the fact that these simulations particularly take extremely long, and most importantly is it's always a surprise what comes out of the box. It takes a long time, and only right at the end do you actually know or see what end up, or you know what you got out of the result. And then even if you get a nice result like this, it's still not CAD ready or CAM ready or manufacturable per se. So customers spend then many hours trying to develop something that you can actually manufacture or get at least into a format that you can work with in a CAD package. But generative design has changed all of that. And I want to quickly explain and show that by use of a case study that we've done for a local group, Motsumi cars. We've done this in a pro bono sense, just to demonstrate the technology and use this as a marketing opportunity as well. This is the rear axle and the drive shaft shown here connected to the wheel and the hub, and that being connected to the braking system. So first of all, we had to determine what the loads were for this case. Customer gave us the road wheel forces for a number of sequences or road events. So we used his initial design that he designed himself, added the flexibility of it and all the structural suspension members over here, and took the wheel through the different events. And from that, we extracted all the loads applied to all these interface points where the rest of his components has to interface with this part. What we then did was to develop the design space, and a design space is always needed as the maximum volume where your design may fit into. What you also set up with Apex Generative Design is the non-design areas, like these interface points, which you don't want to be removed, or where you want to retain the flat and sharp machine surfaces. Then it's a matter of defining and applying all the loads, and most importantly, different events, which are different combinations of loads and boundary conditions. And then it's as simple as starting the simulation. And here we see the results progress throughout the simulation and a graph of the mass being reduced. It started off for that complete body is 11 kilograms, and it reduced to the final part below 2 kilograms. A huge saving in material and obviously mass for a sports car like this, which is quite important. And the beauty of it all is the end result is directly exportable to a CAD package or directly to your printer. So you can literally take that result, it's a CAD format, and you can send it off for printing. Here are some elaborate examples. Now, I doubt you will ever see a piston head in an engine looking like this, but it showcases what you can do if you really want to. Here are some other structural members and some interesting hinge components here as well. But then it doesn't all need to be work. It can be quite functional and for fun as well. So these are some examples that I'm regularly keeping myself busy with over weekends. And as I said to a friend the other day, I simply just can't print simple stuff anymore. I have to design something really elaborate because I can, of course. And then also, just because you can, we had the need to lift the desks in our office by a few centimeters. So obviously, we had to generative design those parts. And then as a side note, beware of your load cases. This is a little part that I've developed for a bracket that broke carrying an alarm sensor in my garage. And I unfortunately excluded the hammer load case from my analysis, and that resulted in me losing part of my design over there. Fortunately, the remainder of the bracket was still strong enough to carry the load. All right, so yeah, just an important note on that. So let's go into the getting started and demo time section. So that ends the presentation. What I'm now going to do is move over to our website. On the simteq.co.za website, you can go to training and events. And under training and events, we have the getting started pages. And the very first one over here is the MSC Apex Generative Design Getting Started page. And this is essentially covering the most basic aspects of getting started doing a generative design. I'm not going to read through it, you can do that on your own. But I want to highlight the layout of this page so that you can reference it later yourself, especially when we're not around. There are some one-time setup settings that we recommend. It's all related to using the GPU solver as well as improving the graphics display. So if you click on this little plus button, it will tell you what you should have done when you installed the software to install the GPU service, where to find the runtime libraries that you need to download if you have an NVIDIA card, and what the specific tick box is that you need to install so that it installs quick and the minimum that you need. And then in the application settings itself, where to switch on or tick that you actually want to use the GPU. And this is the one aspect where having a GPU is really, really worthwhile, because it's really much faster to solve these jobs using the GPU instead of CPU. Then by default, and this is unfortunately the same for Apex structures as well, the resolution for graphic display is a bit low. And you typically don't want to see curves represented by polygons. And here we see This is actually what you would like to see, or what your geometry actually represents. And this is where you set and change that. So application settings, tolerances, switch it to fine, which is typically good enough, even large models. But if you do find that your system lags when you try to rotate or zoom in the model, you can reduce the resolution over here. But for general models, I find that fine is quite good enough for the graphics card that I have. Then if we move on, I have a few notes here. So your first generative design. Now this is a list of the minimum steps required to do a generative design. I'm going to quickly work through that. Then there's a brief note on the actual more detailed getting started tutorials and some advanced options that I really do want to cover in this session today as well. But let's get started with the minimum analysis steps required. So only these 6 steps. You typically define the design domain, define what material to be used. You have to define constraints, loads, set up the study, and start the simulation. So let's see what each of these entail. To define the design domain, it can be literally any shape. It can be a bounding box, as explained before. It can be a sphere. It can be an actual part. It really doesn't matter, as long as you have a solid in your model that you can define as the design domain. Most important thing, whatever you chose as your design domain, your result will always fit inside it. The solver will never generate a result that extends outside this domain. Next step is to define the material. Very logic. Only thing here is you need these 3 properties: elastic modulus, Poisson's ratio, and density for the solution to work. And then constraints. Constraints are exactly the same as for linear static FE analysis, in the sense that no rigid body modes are allowed. It's like standing on a chair with wheels, you're risking your life. Even if there's no load applied in a specific direction, movement should not be allowed, and your constraints has to take care of that. Other interesting thing about Apex Generative Design is that these loads and constraints can be applied to any face of a solid, but you can also define solid sections, which we call partitions. Now, these partitions are the exact same method used for general structural analysis in Apex when we define, let's say, hex mesh and subdivide solids into partitions to have the different sweep directions match one another. Now, there's a number of tools available to manipulate and generate these little partitions. And as I said, those partitions can then be used as a volume where the constraints or the loads are applied as well. So the same for loads. Again, remember to include all the possible load cases, even the assembly load cases, which are typically the ones that we forget about and can actually break your design. Quite an important step. Loads in a single event versus applying the same loads in different events. When you apply loads in the same event, they are typically added or subtracted, and therefore they can cancel each other out. And that's a very important point to remember when you deal with loads. Now, when we get to the study setup, this is the last bit, essentially quite simple. After you've defined your design part, simply right-click, and at the bottom here, you'll see the place in analysis scene option. If there's any problem in your setup, maybe you've missed a step that we've covered, you can see that the analysis readiness tab will highlight or open up and indicate any problems that it has found that you have to rectify before you'll be able to set up the analysis. If everything is fine, however, you can proceed to the Studies tab, where as a minimum, you need to define these two settings. First is your stress goal. The stress goal is to say for the specific load conditions and the specific material that you're using, what is the maximum stress that should be allowed in the end result? And then secondly, what are the events that you want defined? If you double click on loads and constraints, you have the ability to create these different events. So important, you don't create the load cases or events during the model setup, you do this in the study. So once you've double clicked on loads and conditions, constraints, you'll see that the first default event is created, which will include all the loads and all the constraints that you've defined. Now you have the opportunity to select and by that create combinations of loads and constraints. You can also duplicate existing events or add more or delete more over here and then edit each of these in this little user interface. But just remember, the limitations and the requirements are exactly the same. There has to be at least one load applied. If there's no load, the event isn't valid. And regarding the combination of chosen constraints that you define, it still has to eliminate any rigid body modes. And then you're ready to run your first simulation. And this is simply done by right-clicking on the generative design scenario and clicking run. And now you can sit back and relax and enjoy the entertainment. This is the beauty of generative design. The fact that you don't, that your computer isn't busy and you can't do anything, you can actually see the progression of the development. You'll see that the first iteration will appear and it will show a result. And the next as it progresses. And while this is busy running and developing possible designs, I urge you to have a look at these red indicated areas. These are some of the useful things to play with while your results are being developed. Over here, you have the opportunity to change the property that is displayed as the fringe, or pick a property that is applied in the graph. So in this instance, we see that the mass reduction is indicated over here. At the top here, we have some options to record a video, save a screenshot, manipulate the lighting conditions, as well as the background image or background color for this model. Especially useful for reports, for instance. And then at the bottom here, you have a number of options as well, with the important one to note is the last one, which actually gives you the opportunity to export an STL file of the current or any iteration over here. So not only the current and active or last resolved iteration, you can literally take any of these iterations, select it, that iteration will display on the screen, and you can export the STL. You can export it for use later as a new design domain or for any other purpose that suits your needs. Typically, you'll wait for the later iterations, which are more refined, have a better resolution, and where the remaining flat and sharp surfaces are reintroduced. You'll see that the initial iterations don't bother too much with the original sharp edges and machine surfaces, but that the later iterations, they will actually be reintroduced. So that covers the minimum steps required to get going with Apex Generative Design. For better and more in-depth tutorials, I really recommend working through the built-in tutorials that are available. The first is available under the Help Getting Started section. This opens up a browser with a file that you can download, video that you can play to show you exactly all the steps required. But then most importantly, and this is the step that very few people know about, is this section over here. It doesn't only contain more tutorials, it also includes the detailed documentation on Apex Generative Design, but that is online. Whereas this initial page and video and file is installed with your software, the documentation over here is actually online. That will probably change in the next release or so, but for the moment, that's how it is. Now, once you've opened up that link, you'll get to a page that looks like this. Section over here that I'm highlighting is documentation and more information, but over here is the list of tutorials, and you'll find that to be quite comprehensive. So if I quickly swap over to that page and specifically look at the tutorials, you'll see that there's some examples on a bookshelf, a jet engine bracket, a generative design bracket, a bridge, a bicycle pedal, again, some bookshelf, but specifically focusing on restarting and optimization. So that's quite useful if you want to use one of those initial or intermediate result sets as a starting point. And it also gives you more information about more advanced settings and how to manipulate the refining and the density options. There's a two-stage optimization indicated here, how to do part consolidation, how to transition from faceted geometry back to NURB surfaces, etc., etc. And then it's also worth mentioning the command line optimization, which is the ability to solve generative designs without using the user interface. That's very useful if you want to set up a batch of results. Maybe you want to investigate the impact of different settings and you want to run all these analyses overnight or over the weekend. The command line is your friend, and you would like to know more about that. All right, so that's the important sections in the documentation. Let's quickly move on to the section on the web page under advanced options. And I'm highlighting here 4 areas in the documentation that I found quite useful. The first is how to install a material library. This is a little script that you literally download, again from the documentation, and you simply run it as a macro in Apex. This then sets up this list of materials, which are the most common 3D print materials. You'll see some FDM materials, plastics in here, as well as some of the metals. That is quite handy if you just if you don't know what these typical structural mechanical properties are. And this you'll need to run every session if you need, but there's also another block where we've indicated how you can run a script automatically each time you create a new or open a new session of Apex or create a new model. So if that is of interest to you, please contact us and we can assist you with that, or simply follow these steps. Then there's 2 settings. When we go back and we look at the tutorial or the simulation setup over here that we haven't talked about, and that is the strut density and the shape quality, as well as the complexity settings. So let's quickly go through those. When it comes to strut density, you essentially have 3 options: dense, medium, and sparse. Now, at first, you don't necessarily see the differences, but the dense option looks much more like the roots of a dense tree, whereas the sparse option gives you fewer branches but thicker ones. So there's a trade-off, but all three options will be valid in terms of the maximum stresses that the models will see. However, I did find that the sparse design is typically lighter than the dense one, whereas the medium one isn't necessarily heavier than the sparse one. So what is nice about this is that it gives you, as the user, choices. So it doesn't lock you into a specific design. You can look at these and say, I don't like this purely from an aesthetic point of view. Structurally, both are sound, but you can choose which one you want to use. So density is the easy one. Complexity is aptly named because it's actually a complex one to explain, and it took quite a number of support calls to the development team from my side to really understand how this works and how to use this. At first glance, it may look like the higher the number, it's simply more complex. Now that is true in a sense, but this is actually a unit of gigabytes, and it refers specifically to the memory available to the GPU or the CPU, depending on which one you're using. Now, it's not as simple as just simply setting it to the value available on the hardware. A rule of thumb is that you can make it twice as high as the physically available memory. So if you go into your task manager and you click on your GPU, you can actually see the amount of memory utilized as well as the amount of memory available. Now, the rule of thumb is that you can set that complexity value to double what is available. And the reason for that is that that value that you reserve is essentially what the solver then takes and calculates what the highest resolution is that the result can develop into if it didn't remove any material. So it's very unlikely that you'll ever sit in a scenario where no material is removed, and it will typically be far more than 50%, but 50% is a good start. So then, as you progress through your analysis, you can monitor this value and check, do you get close to that value or not? What will happen if this value exceeds the available amount of memory? Your solver will automatically drop back to the CPU, which has more memory available typically, which will of course be much slower. So it's not really a problem in the sense that you will still get your result, but from that point on, you will just wait much longer for your result. The other useful option to look at the memory used for a specific analysis, because this value over here in the task manager is only the instantaneous value, is to actually look at this log file. Now there is a GD engine log file. Now this changes from version to version, so the previous ones looked a bit differently, but for the current 21.1 version, this is what it looks like. You have a folder in your working directory with the name of your model, and then there's a subfolder with the name of the scenario, your study. And in that folder, that's where all the intermediate results are saved, as well as this GD engine log file. And if you look in this file, you'll see these blocks of data. It shows the iteration that it was at that time and the amount of dedicated memory that it used. Now, as long as this value is below the available value, you will be using your fast GPU. So you just want to monitor that you don't reach the value. But if you see, like in this case, that the value is still far below what is available, you know that you can increase the complexity value that was set over here to a higher value, meaning you may end up with an even higher resolution end result. Again, this is not that important for your initial developments, but it's very good to take note of when you get into more detail and you want higher and better designs. So lastly that I want to cover is just some mentioning of some of the other topics available in that documentation. Just to clarify, part consolidation, the part consolidation tool merely provides a quick method to create a bounding box around a selection of parts. It isn't doing anything much more complicated than that. It purely gives you the ability to create a solid that includes all the parts that you've selected. It's a regular solid, it's rectangular, it's aligned with the global axis, but after it's created, you can modify it as you wish, rotate it, translate it, change it, add holes to it, add Boolean solids to it, anything you like. It's purely just a quick way of creating that bounding box. So nothing fancy there. Then there's a few interesting ones. Machine allowance. Now, typically, if you have interfaces where your part has to be bolted down or bolted to something else, you probably want a very smooth machined surface and not the typical rough surface that a 3D printer produces. The machining allowance tool allows you to define areas where the end result should include an extra bit of material, knowing that you will be machining it back off. So it takes that into account. What the axis region tool does, it allows you simply to create solids very easily that you then subtract through the Boolean operations from the domain space. It doesn't do anything more elaborate than that. It's purely a quick way of creating a solid that you can subtract so that you have a space available where the bolt needs to be pushed through the whole design into the actual hole. So it's just a tool to help you define those areas where no material should be. The clearance region is very similar. It's the opposite of the machining allowance tool. So instead of adding material, it removes a little bit more material in certain areas. So where you know that the two surfaces should be able to move past one another with some clearance, you can use this as a quick way to define that without needing to go through complex geometry manipulation tools. And then just lastly, a reminder of the command line options that gives you the opportunity to submit and modify jobs through a text editor and submitting them without using the user interface. All right, so that brings us to the half hour that we originally planned. So I will continue with some demonstrations if there are any interest in that. And I would also like, before I do that, just give you the opportunity to ask any questions. Are there questions? I don't see any hands raised, so I assume there aren't any questions. I just want to make sure that you've created or submitted your poll result. Yes, JP, I see you have a question.
Hi, Paul. How's it going?
Very well, and you?
Good, thank you. So my question is more related to post-processing the STL into a step. So we've discussed it previously, where I've had some issues with the conversion of the result that I've selected into a step file. Even though the step did work in the end and was extremely large, I wanted to know if there's been any improvements in how that functions today.
Yes, absolutely. The first improvement that you will see is the, and let me actually not lie to you, let's actually go to the online documentation over here and go through the listed what's new options. And over here somewhere, they should have, no, I don't see that now. I thought it was published over here, but they've made a tremendous improvement at first, at least in terms of the time that it took to actually generate the facet geometry. So those of you not certain what we are talking about, if you have your result available, and let me just quickly show it by using this example. So if you now take any of these cases, so remember, as I said, each iteration is a design in progress, and you can export that as an STL. So if you typically take one of your later, more refined and smooth steps, and you export this as an STL, right, you can import that STL and manipulate or convert that to geometry, right? You can do it on the fly. It's actually a session on its own that we can talk a lot about. There's some interesting tricks of the trade involved there, but essentially what it does is you have the ability to either import it and have it automatically converted to facet geometry, or only convert it to a mesh, and then you have the ability to modify it and then create facet geometry from that. But then at the end, you have the option to generate NURB surfaces. Now the NURB surfaces are typically your step files, your parasolid files, those kinds of geometry which are easily editable through Boolean operations, using the push-pull tool, for instance. The facet geometry can be manipulated as well, but not all the geometry functions are always selected. But JP, in short, they have definitely made a lot of improvements, but there's still, some tricks to the trade. But the first thing that you will notice is that from the documentation that I saw, that they claim there's a 70% performance improvement just in terms of the time that it took to do that conversion. Do you have another question?
I do. I want to thank you for clarifying the complexity settings, because it has actually plagued me for a little while. The question though is that, so I've run it on two machines, one being my local machine, which doesn't have obviously a graphics card in it. It has a an onboard Intel graphics unit for rendering. So you can't really use that for doing anything. And then, I have another beefier machine, a high performance machine that we use. Now, the results I've achieved between both are significantly different, where the simulations I've had to run on my local machine I've abandoned completely. The question is though, if I do double up on the RAM capability, as you've indicated in your presentation, I didn't do that because I was concerned that my machine would crash. Is there a risk that it will run out of RAM and then possibly crash if I set the setting to double the available capacity?
That is a good question, and I haven't tested that. What I did see on my machine, for instance, is there's a Windows process that pops up and stating that your system is running very low on memory. I haven't managed to crash the system yet, but then on the other hand, I didn't try very hard. So I just know, obviously, as I stated, that if you exceed the GPU memory, it will fall back onto the system memory. But I haven't tried to overspec the system memory and see what it does.
Okay, because one thing, my concern is that then there's limitations there, which, you know, is more of an inquiry as to if they have alternative solutions for those that have less beefier machines or PCs that can, you know, really exploit the capabilities of the software. Where there are limits on high performance computing machines, you know, it's a concern. Then I have a final question, if I may.
Yeah, sure.
Cool. Okay, so a part and parcel to this is obviously validation of the structure, and you know, I've been working through the online Confluence tutorials, and there is a process defined where you can take your results and run a Apex reevaluation. My question is, have you done that? And, you know, given what the definition is of the stress goal in Apex Generative Design versus the actual stress that unit will see, have you looked into that? And is there concern regarding this whole average stress goal versus in reality what the actual stress the component would see?
Right. So first of all, it's important to understand that the technologies are different. When you do a solid finite element structural analysis, I mean, that's as accurate as you can get. The technology used in generative design is similar to voxel meshing technologies. So there is a difference in the actual stress result. But that's the reason this technology is so fast and why it can spit out results so quickly, as you've probably seen, you know, through the first iterations up to the last ones. So the results aren't absolutely the same, but it's definitely a ballpark in the same region. So the idea is to get a design candidate very quickly and then fine-tune it from there on.
Cool. Thank you, Paul.
All right. Are there any other questions? Okay. So if there's no more questions, let's run through a simple example throughout the next 15 minutes that we have available. All right, so I think you got the idea of what a complex model can look like. It can be much more complicated than this, but it doesn't really have to. So I'll open up a new session and start the model from scratch. Okay, so I'm just going to import some basic geometry that I want to use as my domain or design space. So this, as I said, could be any shape. It really doesn't matter, but I'm going to use this one. Okay, so I'll define this as my domain that I'm going to use for my design. So now I see the design part is defined and I have a design space. I need to define a material. I'm just going to define some steel here. You see, I haven't run the script. I could have. Sorry, what I missed here. Okay, and let's assign that to the part. Okay, so there's the 2 steps done. Now we need to define constraints. I'll just use a very simple fixed constraint. We'll fix it to those faces over there. Just to get started, we'll look into more of the advanced options and settings available later on. And let's apply a few forces. So I think what I'll do is I'll apply a force in the y direction over there. I'll apply something in the Z direction over there. And let's do something interesting. Let's do a moment Z-axis on that face. All right, so now I have 3 loads and boundary conditions. That should do it. If I have missed anything, Apex should be telling me right about now. If I did, and it says there's no offenses found, the model is ready for analysis. So I can move on to the next step, which is to create a simulation scenario. Just be aware it might have these default studies in there. Don't worry about that. Just worry about your active study. You can actually delete those if you want or make changes, but the important one over here is you know, all these settings that we talked about. Let's first just dive in, set up a stress goal, and let's maybe create few events. Otherwise, my loads will purely be summed together and apply a single resultant load. So I'm just going to quickly duplicate my setting of my events 3 times. So for the first event, I'll include the first load, but all the constraints. For the second one, the second, and for the third, the third. And that's all I have to do. So there, now I have 3 events with different forces and the same constraints. The one setting that we haven't talked about, and it's maybe worthwhile mentioning over here, is the ability to specify whether or not it has to keep the areas where the loads are applied or not. So for instance, if my design is such that it's fully capable of carrying the load by only using 1 or 2 of these attachment points, I can allow it to remove that one. So in this case, this is, now I'm actually not sure which one that is, to be honest. It's that one. Okay, so I can tell the software, I'll allow you to remove that load application area. So you don't need to put in material in here if you don't need it, but I do need those 2 attachment points. All right, so you can see the thumbs up there. This little man is available. And now let's start the simulation. Now this is the point where you grab your cup of coffee and sit back and enjoy the view. So at the bottom here in the status window, you can see the simulation is starting. And it's going to run on the local machine. You can set it on a remote machine. And now the user interface adapts on its own. You don't need to do anything. And there we can see the initial design. And it's quickly developing into something else. Now this is the time to start investigating what's happening in the user interface. There's a convenient little box over here, especially helpful if you start losing yourself or you're not sure how does this relate to the original domain, that you can switch on the initial block as a transparent block over here, so you can see, okay, this is where I am, this is where I started, this is where I'm at. Remember the stress goal that you set and compare that to the actual stresses defined here. So as long as the stress over here is lower than the goal, it will keep on removing material until the stresses raises to that level that you specified. Then it actually has the ability to revert back and add material again. So that's maybe a good point to raise here as well. Generative design doesn't lock itself into a branch of development. If it sees that it has now removed material, but the stresses are increasing beyond what is acceptable, it will actually come and add material back. It will just never add material beyond the initial domain that you specified. But there are nice examples of where it removes removed material, the stresses developed higher, and it actually brought back or reverted back to earlier designs and brought that back. Some of the other settings that you, of course, have available that I've mentioned, I haven't employed here, for instance, is the ability to define areas that it has to retain material. So at this stage, I didn't specify that this ring or section of the model has to stay intact. So at this point, it is allowed to remove a portion of the hole where the constraint is applied, and the same for the area where the loads are applied as well. So if it feels that it doesn't need that material to carry the load, it is actually allowed to remove it, or through defining that non-design spaces, you can ensure that there's always material, regardless of what the stresses are in that region. All right, so on the left-hand side over here, we can monitor the stresses, or the maximum stress at least in the model. And you can see progressively through the different stages, the stresses actually increase since we allowed a value of 10 megapascals. The maximum stress is now only at 3.6 megapascals, so it will probably remove even more material. Simultaneously, we can also look at other characteristics like the design mass. We can see the initial design was close to 4.4 kilogram, and it's already below to almost close to 1.5 kilograms. Important to note that at certain iterations, the resolution increases. So you might see weird interim results that look like it's got some thickness, like, you know, these little bumps. But in the follow-up iterations, those typically disappear again. So don't worry if you see strange results. There you can see now those lumps disappeared in the follow-up run. And you will see cases like that further on as well, each time as the internal mesh generator reduces cell size and increase the resolution of the result. So you sometimes at that jump, the initial value may look very blocky, but then it resolves itself quite soon. So the neat thing here is, even though we've chosen the setting that will take it up to 64 iterations, and as you can pick up that progressively these iterations takes longer, we already have an idea of what the result is going to look like. So this is quite useful to identify mistakes in your model setup. For instance, if you saw that you know, the stresses doesn't make sense for one of the load cases, you can actually go in and switch to a specific event. So now we only see the stresses for event 1, or let's have a look at event 2, or even event 3. So we can see that event 3, which was that moment that I've applied, actually causes high stresses in that area. And of course, if we switch back to all events, we see this combined effect, essentially, of the different load cases. So this is useful to pick up on any mistakes that we may have made during the setup, or if there's something that we realize, you know what, I would have preferred a different result for some other reason. This is the time where you now have the opportunity to terminate your simulation right here and go back to the user interface to make the changes and modifications. And I think that's it for today's session. You're more than welcome to ask more questions. You're more than welcome to contact me. If you have more questions that you'd like answered. Otherwise, yeah, go and have fun and design some brackets for use at home at least.